Good afternoon, good evening, good morning, depending on what time zone you're in. The topic of the talk today is revisiting the Casimir effect, which is something I've addressed at least twice in some detail. And precisely for that reason, I'm hitting a little bit more in some of my more recent work on special relativity, which is directly relevant to the Casimir effect, but also gives a different spin on that. So if you're looking for a somewhat different perspective on some issues about special relativity, you've come to the right place because there are some interesting differences here. Deeper problem with the Casimir effect. Casimir effect, just as a very brief introduction, is the idea that if you put two metal plates together, there's a pressure that pushes them closer and closer together. And in doing so, this force is supposed to show the almost infinite energy that resides inside of quantum uncertainty. So it's a famous effect and was supported actually strongly by Bohr, although Casimir is the one who did the experiments. And it has had quite an impact on physics over the years. So taking a different look at how space-time is structured becomes very relevant for how this Casimir problem, how the Casimir effect works out. So this is the first dive, is to go into something called state machine universe. The premise is quite straightforward, that underneath space and time, rather than having a space-time fabric that simply resides there and exists, a very pre-existent kind of concept of that. There's another way of interpreting the universe that in many ways is actually closer to everyday perceptions. We talk about physics as the rules by which matter behaves and energy behaves. And even making that statement is actually a statement very similar to what in computer science is called a state machine. That is, you have a certain condition, you have a certain situation, you have a certain status, you do an operation on it, you apply an operator, and that transforms that matter into a new state, into a new version of the system. So this is actually a quite intuitive concept. It's not a concept that's difficult to understand, even if you're not from a computer science background. It is the fundamental concept behind computer science. Every computer is a state machine. It has a memory. You have operators that you apply to that memory, and they change the state of that machine. And then you continue in a sequence to get the overall results that you want from this. In physics, however, there's a tendency to have models that go beyond the simple statement of transitions under the rules of physics. You have definitions of matter and energy that extend for all of eternity in some cases. You have the idea of what's called a block universe, in which everything is predetermined, preset, and many physicists have a lot of discussion about how now even exists, how the concept of what we're doing right now exists. Experimentally, that doesn't happen. Experimentally, you know that you're watching this right now. You know that certain things are happening from your perspective. You have a very definite idea of what is right now. You make a strong distinction between past and future. So state machine, as I say, in some ways going back to a more intuitive concept of how physics operates. But the particular version of, in this particular version of the state machines, every inertial frame, rather than being a separate concept of space and time, something that extends to an indefinite length, it becomes a subset of how the state machine works. When you do this, it has a curious effect of making the concepts of space and time into behavior patterns. You don't have this idea of a fully extending future, a fully extending past. You only have this idea that if you have certain sets of operators that work in a certain way, you wind up getting a behavior that we then interpret as time. So this is a very immediate and very kind of a pattern type of interpretation of how you do that. At the large scale, a state machine model still gives you the kind of large scale only, not quantum, but it gives you the same kind of deterministic behavior that you expect. So this is not incompatible with the idea that you have a well-defined future for things like orbits, that you have certain patterns that can be predicted over very long lengths of time. However, it does change the way that you interpret how that happens. Instead of saying that that long-term pattern already exists, you're instead saying that you have operators that will persistently behave in a fashion that allows that future to be predicted. When you go this way, this idea, and I think most of us have this, we have this idea that we're kind of trained into it informally, is that space-time together is a fabric. It's an actual substance. And not accidentally, Einstein very much pursued this approach in his later years. In his early years, he did not. But in his later years, he took space-time not just as an idea, but as an actual fabric from which everything was composed. And that remains a very common approach in doing these. In terms of experimental, that's a different issue because experimentally, you must have actual material objects before you can measure things like space and time. And I'm trying, there it goes. For some reason, I could not get my button to go down. Okay, so I'm saying that a space-time interpretation, you can take the entire universe, uh, take each piece of it as an existing state of the universe, and then that you have some kind of operators that you apply to that to go to the next version, the next iteration of the universe. Now, the unit that turns out to be extremely useful for doing this is what I call a distance activity unit. This is an invariant arrow that essentially is attached to every unit of matter that you might want to define. The unit of matter can be pretty much any scale. You can have something that can be as small as a particle, it can be as large as a galaxy, and you can have a scale in which the time involved, which is the main metric that you use to define the length of this. The time metric could be an extremely small unit of time, a very large unit of time, could be a million, it could be a million years, a million light years. You can have also very small nanosecond particle type things. The scale itself doesn't really matter. The idea is that if you have a unit of matter that can be defined as a well instantiated unit, something that persists. So you have an object. This is very much the object idea. A star is an object. A block of matter that is moving through space is an object. Anything that has that kind of unity where you can define it so that it goes through a period of time has this ability to have a transformation that can go in a number of different directions in the future. And the directions are the angle of this arrow, so that you move the angle. If you're in one place, you go strictly into a pattern that we'd interpret as time. Whereas if you go in another direction, you can go ideally, you can't, it takes infinite energy to do this, in a completely straight line, which is the same thing as traveling at the speed of light. Now notice there's no light cone in this. This is just talking about the transformations that you're doing to the state of that unit of matter. That's a different thing from saying the actual, you're not trying to track the light cone aspect of this, but rather the transformations that you're applying. A useful analogy in this, interestingly enough, is this idea, and I can't help but reference the movie Speed because it just gives a delightfully appropriate example. You've got somebody stuck in a bus. The bus cannot slow down. It always has to go somewhere. So in some parts of the movie, they're just looping around and going in a circle. Then in other parts, they have to go in a straight line. But there's always this constant speed that is trying to drive this bus. Well, it turns out the relationship between space and time, between time and space, between time and distance, works very much like that. You have an unavoidable activity, which is the looping part. That's where you can actually do something, where you can change state locally, where you can turn the dial of a clock, where you can watch something and observe it. There's always a cyclic aspect to any kind of time measurement, which we see very literally on time dials. But on the other hand, you can take that same motion and extend it out all the way to the right, transform that into a distance. And that's where you go at the speed of light and time comes to a complete stop because you've used up all of your internal velocity, not for the activity part, the coiling part, the looping part, but you convert it entirely into distance. Now, what's interesting about this structure, about using these ideas of DAU units, is that it immediately gives you the results of special relativity that are often done in a much more complicated fashion. You have an angle, and the angle tells you how much you've tilted the operator, the next iteration of the state machine for that object. You can have it go straight up, in which case it's pure time. You have the fastest clock of anybody around you. The clock just keeps on going in a circle, but you can also stretch it out to different angles and go to the right or go to the left. You have a choice on that. And by the way, notice the theta convention, I put a plus sign there because I am using the reverse. These are the clockwise plus angles, which is a little different from some of the other representations. So just in case you want to get picky about that, notice that it is a plus in the right-hand direction. So you go all the way over to the right, and the state change that you induce on that object is purely one of translation, of moving to a different point in space. If you're familiar with the concept of an interval in special relativity, an object that moves at the speed of light is said to be, in some sense, simultaneous or in the same location. Um, Now, the interesting thing is, we know that's not really true, because if something's moving at the speed of light, yeah, the time stops, but it also changes the distance. So this simple rectangular representation actually captures that quite nicely in saying that, yeah, the time stops, but that's not the whole issue. The only way the time stops is if you convert all of the DAU iteration, the operator becomes entirely a distance-like operator. And this was something that the YouTube channel Itane-san pointed out to me, about how there was a simple relationship between space and time. And I loved it as soon as I saw it, because this literally converts the concept of space-time interchangeability not into something about hyperbolic surfaces or anything like that, but really just sine and cosine. So you have a different relationship between the space and time that always has this very fixed relationship to this invariant arrow, your operator for how you change the state. Here's a more detailed example of that same idea. You have a cluster of operators. They're all going in parallel. They all start from the same definition. They all have a shared definition of a clock state. They have a time at the beginning. Then they have a time at the end, the DAU state 1, and that's the one. But if they check their clocks, they do the examination, they find, yes, we all still had the same clock times. So they say that we have a shared definition of what time is, and also of what space is. Their separation between them, because the arrows have remained parallel, stays the same. So this gives you pretty much a definition of what an inertial frame is in a state machine model. So an inertial frame is simply a bunch of arrows that share the same operator and share the same starting point. That seems like a simple thing, but it's remarkably powerful for analyzing more detailed examples of how this works. And to get into an example of that, this diagram, in some ways, I like this diagram because it's really kind of trivial. It's not a big deal, but it also contradicts in a subtle way a century of how we've tended to interpret special relativity. And the subtle difference resides in that point. I'm not even sure if I can do, okay, I don't know if you can see my arrow or not, but that little pivot point, that little round black circle, is over on the front end of some object. It's defined by these 4 arrows that I have in gray. When you tilt that object, you have to actually put these operators up into an angle. You have to do some changes here. So there's a pre-acceleration phase that I'm not really showing here, but it takes some time simply to get these operators in place. Showing a state machine representation of acceleration just almost immediately, it does immediately give you much more information about what has to happen to the objects involved and how the process of acceleration works. It is not a simple boost. It is something quite a bit more complex than a boost. And that's one of the reasons why with this model, you can start making some inroads into complex problems where you have multiple inertial frames interacting, that you can make more specific predictions in some cases of what's going to happen with this. So that's where you get the overall model. You have a universal state machine. You have a bunch of clocks that are all going in parallel. They're all saying, we're going to do the same thing. But then you have this outlier here who's going at a different angle, in this case, a 60-degree angle and from vertical. And that clock winds up getting half speed because it's using a lot of its energy, all of its motion through time and space to move laterally in the state. It's changing its location in the state machine as opposed to simply iterating within one single place. So this is where I say this is not a space-time model. What you have here is you have fermions, especially. If you don't have fermions, you can't do this. So you can get all the way down to the particle physics level. If you just have bosons, bosons are part of the time equation, but if you don't have these gnarly, strange little particles called fermions, which is to say electrons, protons, matter type particles, you don't get this property of where you have this nice little separation and this change of state. So these become the fundamental units of memory devices, is the fermionic states of universes. Those are very limited in number. I've also had previous presentations on the idea of a sparse information universe. When I say a sparse information universe, when I talk about fairy dust as information that doesn't really exist, this is exactly what I'm referring to. I'm saying that the fermionic content of the universe defines an absolute, inviolate limit on how much information you can store in this universe. So you can create more pairs of fermions. You have a certain amount of energies. There's some fungibility between energy and fermionic memory. But if you don't have this, you don't have a definition of space or time. Now that's, I guess, a very different concept from saying that you just have a fabric and then you start playing with the fabric. It says, no, no, it says the fabric starts and is defined and is limited by the existing matter in the universe, and that all of these concepts that we think of as space and time and distance are nothing more than relationships between these fermionic units. The relationships are complex. In fact, I think one of the most interesting places to explore this model further is how these relationships work between the fermions, how they define in particular the concept of distance. Because in some sense, they don't care about distance, which is remarkable. But in another sense, they care very, very much about distance. They define these relationships, and we are trapped within those relationships. But if you talk about issues like entanglement, you talk about these strange effects that you get in quantum world, that's where you're peeking below the surface a little bit. And you're seeing that these relationships are constructed from the fermionic matter. They're not just a given. So again, universe is a state machine, drives you to the idea that space and time are not just only transformation operators, they are finite and limited and scoped transformation operators. You have a certain set of matter, you have a certain set of options for how you can define space and time, and that's it. If you try to talk about space going beyond that, it becomes a meaningless concept. You're trying to do operators on memory devices that don't exist. So you need your memory devices in order to get these concept of transformation operators. There's a lot of power in that model. If you think of it as flipping things upside down a bit, you start with the memory devices, and then you develop different types of space-time, because one of the things that happens with this model is you have more than one version of space-time. If you go back through some of my previous presentations, I've talked about things like the rotational states of space as being actual states of these operators iterating on certain subsets of the memory. Overall structure is very simple, very computer science-ish. So you have one DAU per item per global iteration. You can define your DAU unit to be any scale you need, depending on what you're looking at. So you get easy distributions of size depending on the size of the units. If you have a galaxy is a well-defined unit. You can have one Dow that has 1,000,000 years as the distance between states, and you can have 1,000,000 light years as the corresponding unit of the Dow tilted all the way to the right or to the left. So left or right being of course, all of the possible three-dimensional directions. So an oddly simple model, but one that puts state-machine interaction, state-machine dynamics above concepts of space and time in terms of how fundamental they are. There's a simpler way to visualize the same thing. I've used this before. This one, I just like it because it is so easy. It's like playing with blocks. You take that cluster of arrows I showed earlier. You say, well, I can tilt it one way or tilt it the other. The instant you tilt it, that defines the front of whatever the system is that you're trying to accelerate. So this is where the idea that the front of the object, the leading edge of whatever group of units you're accelerating, becomes extremely important because it drives the transformations that you have to do on the rest of the units. And again, in terms of state, this transition tells you pretty much everything you need to know just from this little tilted block. Actually, it does tell you everything you need to know about Lorentz contraction, about time dilation, and about some other effects that can get a little more exotic. But those are all in there. One of the more exotic effects is time gradients. Einstein talked about them but didn't quantify them. This one quantifies them. The tilted block also immediately avoids time paradoxes. Why? Because everything still exists within the same time as the rest of this system. You've still got the other objects moving ahead. So you've just tilted and changed the state of this one group of objects. Now, within that group of objects, that's where you have the remarkable ability to define a space and time in which no experiment can tell you that you're not the same as anybody else. This is the old equivalence between inertial frames. That's still there. What the state machine model does is it says, no, 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 you can't just extend that arbitrarily. You cannot just say it applies everywhere. You can create these new spacetimes that have these marvelous properties, but they're also finite in length. So you tilt 3 cars in a train, you accelerate the 3 cars in a train, you sync them all up. That's all you get. Everything else becomes relativistic Doppler effect. Everything else becomes just how you interpret the outside data. You're not changing the outside universe, which in many ways is just common sense to say, well, because I accelerate it, I don't change everything else. I don't slow down the rest of the universe. The rest of the universe could care less what I've done. The operator dynamic, tilted block dynamic, immediately shows you that. Here's just 3 examples of that. And this is, again, where I point out that these tilted blocks are remarkably powerful for telling you what the transformations are. You find out that when you accelerate the object, you have to begin with a set of clocks that have certain values, and these values correspond to the locations in the embedding space. You have this embedded space that still has the same time and space definitions as ever. You're the subset. You're the guy embedded in that space. So the train embedded in that space follows these rules, sets this up, and here's the kind of results that you get. So after one DAU for this group of objects, you wind up with these different results. So you find out that you have your non-simultaneity of the front and back of the train. You have your Lorentz contraction because you actually change the state where these things have to be smashed closer together. And the exact amount from this tilted block is the same thing you get from the relativistic diagrams. It's just simpler math, which is a little bit of a hint. The fact if your math simplifies that much and you get exactly the same result, you want to pay attention to that because it's saying something about maybe you don't need the hyperbolic stuff. Maybe you don't need quite as fancy of a structure as you thought. This is a one that I've done. Hello, Bill Slater. This is the one that I've shown a number of times and will continue showing because it is just so important to understand this. Acceleration is not just a boost. Acceleration is not just a second derivative. That is an oversimplification of the math. You must look at the physical state changes that happen in the state machine. This is why I say state machine representation is more powerful because it tells you what you have to do. You have to select a set of objects, finite. That's an irreversible choice once you make it. You have to physically squeeze them together. And if you do it in satellites, it makes it really apparent. It's not something that you can, when it's a small object, it's easy to fool yourself into saying that, well, it's all just a transformation of state. It's not. If these satellites are a light year apart, it can take you up to a light year to get them in the proper position. And all of that has to be taken into account before you can actually accelerate the object, which is remarkable. That's not just a simple, smooth differential boost. That's something much more complicated. You'd have to reset the clocks. And the example I've given before, I find this amusing, is that it's no different from setting clocks when you have daylight savings time, where you go one way or the other, depending on which season it is. You move the clock ahead in the back of the train. And this is so literal that you could actually have in a large enough train with a large enough acceleration, you could have an actual human being in the back of the train physically adjusting the clock and say, okay, it tells me now that it's 1 o'clock and it was 12 o'clock. That's weird. And because he didn't see an hour go by, he just reset the clock. And it's important to understand that difference because that's where the time paradoxes disappear. Because you realize that the elapsed time is still exactly the same as the embedding frame. You haven't lost, you haven't created new time, you haven't taken time out somewhere, you just reset the clocks. And then the final stage in this one is to actually send it, to actually accelerate. So again, easier to show with satellites because in satellites, you do have to independently accelerate them. If it's an actual train, you're pushing it. So it's easy to skip over that quote detail. But these are not details. These are fundamental to how this works. And the state machine approach shows it very clearly. A differential mathematics only model makes it so easy to skip over these critical steps. When you take this structure, and this one I've talked about before, talked about it last time, but this is moving in interesting directions and fairly quickly. I did not know that there was an imaginary plane representation of this until I was going through the math and coming out like, oh, all of this is just one complex number multiplication or rotation in complex space. Really? It's kind of like, okay, how did that get so simple all of a sudden? And yet that is what you're doing. This is essentially a tilted block diagram, picking in on a single point and then translating it into imaginary real-time real coordinates. One of the things I'll be experimenting with in the future is I think there's a very, very interesting quaternion connection. If any of you listening to this are quaternion fans, you should take a look at this because quaternions have been frustrating people in special relativity for literally, I think, a century, almost a century, because they seem like they're the right idea, but they're Euclidean. And of course, you had this whole thing about Minkowski's signature with the mixed signature. This flips everything back into Euclidean. So all of a sudden, the idea of quaternions to represent the three directions of space, and then in that case, this real axis, the time axis would become the real axis because you still get the same rotations. So there's a fascinating potential here to use quaternion math and also octonian math for those of you who are into that sort of thing. Octonian math also has some really interesting prospects because it includes the idea of momentum space. So I'm going off on a little math tangent on this, but there's just some really, really interesting mathematical possibilities for exploration in terms of representation of the state changes of a machine. And they involve mathematics that many people have tried to use for a long time and had mixed success. Sometimes it seems to work, sometimes not. I think part of the reason why they haven't worked is this bit of confusion about the mixed signature Minkowski space. Is this a simulated universe model? I've been talking already to say this is all just like a computer. Yeah. Well, no, it is not. In fact, it's really very, very different from simulated computer models that pretend that there's a computer somewhere. This is the computer. The state machine is reality itself. You only have one instance of it. It's not running on some separate substrate. It is the substrate. It is the state machine. It is the set of rules that apply that you get these transitions from one state to the next state, one DAU, one DAO iteration each time. So that's not the same thing as a simulate. A simulation implies that you can have a universe on top of a universe. And there's a really dangerous assumption in the simulated universe idea that information is just free. Just any information you want because it's space-time's infinite, infinitely detailed. You can get all these silly ideas that don't correspond to anything experimentally because we never see that. We never see infinite information experimentally. We only see quantum uncertainty after you run out of energy. And it's an important feature to keep in mind, because if you assume that there's a space-time fabric and you assume it's completely continuum smooth, then you've assumed infinite information. We don't see that experimentally ever. Quantum always puts a limit on that, and it's trying to tell us something important. So you get the state machine structure, and you get no block universes. You only got one universe. You barely got enough storage for one universe, because the fermions that are out there that you can count, that's it. That's your substrate. That's your state. And once you run out of those, once you run out of the energy and the fermions that you have, you don't have any ability to create any more information, and therefore no ability to create more, either to extend this universe into a block universe, make these things infinitely long. You also don't have multi-worlds. You don't have enough information for multi-worlds. It just doesn't happen in a state machine model. Anything that involves loss of space-time becomes this quantum domain. So there's a relationship between loss of information and quantum. It's more complicated than that. There's some really interesting stuff going on, especially given issues like entanglement. But you have to realize that you're hitting a hard limit whenever you get quantum. The reason an electron can't figure out where it is around the atom is not because there's an infinite number of electrons doing infinite things at infinite times in infinite ways, which is, if you think about it, a little strange. Why would you think that? But it's just saying that that's the best the electron can do with the mass and energy it has. It doesn't have enough mass to get any sharper than that. An electron orbital becomes pretty much the best definition of a localized electron you're going to get. You can have a stronger positive charge and make the orbital smaller, but it's always going to look something like an orbital. So it's a different way of looking at that. Instead of filling that space with particles that all take infinite energy to actually instantiate, you just say that doesn't sound right. Let's stick with the energy you have, stick with the detail you have, and realize the fuzziness is due to lack of information. The state machine cannot make something that it doesn't have enough memory to define. Unavoidably, quantum field theory, if you take a state machine approach, quantum field theory gets hit the hardest. And that doesn't mean that quantum field theory is in any way, well, no, I'm going to qualify that. Quantum field theory is one of our best theories we have for predicting any of a number of phenomena. QED is amazing what it can predict. But even Feynman was saying that, he said it's probably more like a checkerboard. It's something, and he derided his own theory just to make this point, is that something's not right when we put infinite energy, infinite mass, infinite information into 1 cubic centimeter of cubic centimeter of space. So one of the consequences of that, where quantum field theory does terrible, is the vacuum density issue, because quantum field theory just has no answer for that. In fact, it just makes some of the most terrible predictions in all of physics. So what you need to do is somehow quantum field theory has to be rewritten in terms of a state machine formalism. And I think that's a fascinating issue, because you still have to retain, you got to keep the same predictivity that you have. You don't lose what you get in quantum field theory, but you do have to take a different look at it. And you can't just keep elaborating details infinitely down at the bottom. Now, if you notice in model, SMU model, state machine universe uses space as a separation, then time becomes an aspect of that. So does that make space more fundamental than time? Definitely not. The definitions of space are themselves some kind of subtler, more internal looping behavior that is going on and is allowing these things to separate themselves on a frequency basis that doesn't involve a whole lot of energy. When we use frequencies in regular energy, like an electromagnetic spectrum, there's a strong energy component to the frequency separation. Whatever's going on with the separation of the states, of the fermionic states in terms of space, the marvelous property of it is it's almost, not quite, but almost energy free. So you can have this incredible separation at almost no cost whatsoever. So you have this very weak bonding at large distances, but you don't have an enormous amount of energy involved with that. That's really what made our universe possible, is that you could have this kind of extremely cheap separation allows this instantiation of a state machine. So there's some really interesting physics that go on. So the same idea of radio frequencies separate these states, that they have different, they're actually different frequencies. So when you have an object at some distance from us, there is a frequency separation interpretation of that. And we see this in physics all the time, where you always have this reciprocal interpretation of distances. But the cheapness of it is what's really remarkable for the space domain. Postulate, and this is actually an old postulate that I've made, oh gosh, over a decade ago. I don't remember, a long time ago. But the state machine model just makes me want to emphasize it that much more. You have two spaces that are used in physics, especially in quantum physics, which are the location space with time, and then you have the reciprocal space, the momentum space, with mass and energy. Somewhere in here, somewhere in those two, which probably have some kind of octonian representation if you're into hypercomplex numbers, somewhere in those two, there's a break, and one of them collapsed and becomes localized into the energy and momentum component of objects. And the other one expanded and became massive and was able to implement this idea of very, very, very cheap separation. So within this concept of these essentially total of 8 spaces, octonian, the octonian space is the most likely mathematical structure, there you have a fascinating symmetry break. And that symmetry break is fundamental to how we go on doing this. This is a good topic for exploration. Going to a state machine model does not, it changes the type of math you use, but boy, it gives some interesting opportunities to some maths that people have tried and maybe need to try again from a different perspective. Minkowski space is a math error. Oops, did I really say that? Yeah, I did. Minkowski space is not an error in the sense that all the Poincare Lorentz transformations, those still apply. You can go to that new space, that accelerated space, and within that space, you can readjust all the coordinates so that you see your own orthogonal definitions of space and time, and they're just as good as anybody else's. So those still apply. There's no problem with that. However, however, the negative time signature of Minkowski space is, the only way to put this is, it's a math error. It's not fundamental. It is not correct. It produces all sorts of consternation, and you start doing these Zen type operations about saying like, there's no distance between things if they move at the speed of light, even though obviously they're very far away if you move at the speed of light. So you get out of that, and the reason those things pop up is the way that the Minkowski space negative signature was derived. And Leonard Susskind has a beautiful description of this. He really does. I highly recommend this little section. He's a great speaker on these topics. And he gives an explanation about saying, well, here's what happens. You assume that it's Euclidean. You do the transformations that Einstein created. And here's what happens. It no longer cancels. And he shows how you have to use a negative sign in order to get it canceled. And suddenly you come out with the right math. There's a problem. And actually, Susskind states it right at the beginning when he shows his first figure in that YouTube session. He shows the origins having the same origin, and you go like, so what? So what's wrong with having the origins at the same place? You can put the origins wherever you want to, right? No, you can't. And that is what's so beautiful about this error, because it makes it so subtle. Einstein said back in 1907 that you choose a starting point in both systems the moment at which the coordinate starting points coincide. The instant Einstein said that, he hosed himself. He hosed himself for the rest of his life, because by making that assumption, he created time paradoxes. And if you think of those blocks I was tilting earlier, tilting the block into the past. As soon as you do that, you're putting that little origin, you put it in the back end of the block, and then you're pushing the block down this way until it intrudes into the past. And you can't do that without violating causality. So what seemed like an innocent assumption that is a very standard mathematical assumption, you got two coordinate systems, surely they can coincide, turns out to create a paradox that you really then can't get out of. And because it's such a subtle error, it makes it very hard to realize why it didn't work. And you see this in Einstein's own work because he never put clocks at the beginning and end of his trains. I've said this before, but Einstein would put clocks everywhere, except for that blooming train of his. He had this train going by at almost the speed of light, and he wouldn't put a clock in the beginning and end of it. He just kind of skipped over that part. And this goes back to this point, because once you make this assumption, it gets very ambiguous how you define clocks, how you correlate, how you start the clocks. You can say how they change, but you can't say what the original settings are. Tilted block formalism gets rid of that and just says this is just time shifts. This is just daylight savings time stuff. There's nothing profound going on here. You just have to do it because otherwise you can't create the new construction of operators that will then give you space and time-like behaviors. You can see this, there's kind of a graphic example here. These are some of the tilted blocks. They're also very similar to some of Minkowski's figures because he also used these trapezoidal blocks. If you look back at his original work, you have one frame over here on the left. Now notice, because that frame has used the time-only definition of going between the iterations, that one on the left has no problem synchronizing with literally the rest of it. This could extend out to the Andromeda Galaxy. The Andromeda Galaxy is not moving very fast compared to us. So you have this huge domain in which those time definitions apply. Time definitions depend on not moving relative to each other, not how far away they are, but not moving. So if you got two objects that are not moving relative to each other, and they're 10 galaxies away from each other, it doesn't matter. You can consider those to be part of the same inertial frame. So it's a little subtle point that you want to be careful about, that how large is the area of things in which you have things that share that commonality. Now, if you just accelerated your ruler on the right, which could be that train again, all of that is lost. At the boundaries, you get bang, you lose that. At the boundaries, all you can see is the other coordinate system. You lose the ability to extend those rulers beyond that scope. And that's important because it says, again, the tilted block is a finite limit on how far the inertial frame applies. But the more important point, and this gets back to, again, I loved Leonard Suskind's talk about invariance. So, but you need an invariant. How do you create an invariant? How do you create a number that doesn't change? Well, the answer in this case is extremely obvious. It's you use the larger embedding. You use the space in which the object is moving. Because you see those horizontal green lines, they still apply. You can still measure every one of those points and those rulers that are in motion. You can still test every one of them. We usually don't, but you can. And the results as you get it, even if you don't, are going to be the same. So you have a coordinate system in which you do have Euclidean definitions of space and time, which is what this figure is. I've got X along the bottom. I've got time going up. This is Euclidean spacetime. So that Euclidean spacetime can record these events, and that's where your invariant is. So the idea that Susskind brings up about how you have an invariant distance you define in a Euclidean way no longer seems to apply. It does apply as long as you use the larger embedding frame. You get hierarchical spacetime. You don't have just one continuous spacetime for each unit. You have a hierarchy. If you accelerate something, you've created a subset, but the outside definitions still apply. By the way, I have added some slides from the set that I had last night. If you're following along in some slides, a warning, you might want to download a new set. I've added 5 slides, and these last 2 have been a couple of them. But just to warn you, in case you're like, where did that slide come from? This gives you this idea, if you extend it large enough, that you can really go all the way back to something approximating, the cosmic microwave background. The whole curvature of space is a whole other issue. I'm not trying to address that here. The point is that you have Euclidean definitions that can go over extremely large spaces, of many, many galaxies. And you can have at least a concept of a first ancestral Poincare bubble. That is a set of first inertial frame bubble that has all these shared definitions. Well, guess what? You can use that at whatever level you're at to do your Euclidean invariant measurements of the separation between different events. So we do that in a more localized sense. You have your local, your latest ancestral bubble, or local, you can call it a local, but I like to say latest, the last one that everything shares a common definition from which they accelerated. So you use that lab bubble, and you can make all the definitions and create Euclidean four-dimensional space to track what the events are and to say what the distance is between them. Now, do people actually use that? Of course they do. You know, it's intentionally being a little humorous. Do people use lab coordinates? Well, have you ever looked at a bunch of particle tracks from CERN? You're not looking at them in Minkowski space. If you tried to translate that figure into Minkowski space, you'd be spending the next century for each one of the particle tracks on each acceleration trying to redefine what the definition of space and time and invariant is. So of course we don't do that. What we do is we take a picture of it in the embedding space, the lab space, which is Euclidean, and then we have a location of the track. We have a time of the track. Everything's Euclidean. There's no Minkowski. You don't want Minkowski space. It would be a horrific task to try to translate this, and you wouldn't get anything out of it. And again, why is that? Because the Minkowski space is fundamentally a result of a mistake, a small, subtle error that you could infuse origins instead of acknowledging that you have to create subsets. So if you don't have the subset concept and your state transition machine, you can't get this right. I'm going to pick on Minkowski again. Differential geometry. To never let this is okay. This is supposed to be physics, folks. This is, but you sometimes physics just kind of goes to the point of saying, I'm just going to say something. And boy, is this ever an example. To never let a yawning emptiness, let us imagine that everywhere and at every time something perceivable exists. What? What? Why? Where'd you get that? Where did that come from? If you said that in space, you would make every particle into a giant block that occupied all of the universe. Why do you get to do it with time? And he uses this word substance. This is a preference, a philosophical preference, and Minkowski just jammed into it. There's no definition of this that corresponds, like I said, to never let a yawning emptiness. That pretty much summarizes it. He just said it that way. Why did he do that? Because he wanted differential geometry. He was just burning. He just really wanted differential geometry because that was kind of his baby. And this allowed him to create world lines. Once he had world lines, he could talk about different geometries and about the shape of it. This is a valuable mathematical concept. That's not the issue. But the issue is if you try to make it fundamental by adding substance that's not there, then you're actually redirecting from the structure of the universe as it actually is observed. So this is an extension based on preference. This is not an extension based on anything experimental. The implication of this, though, is that even though differential geometry is just so, it's incredibly important also in things like solid matter physics, where you've got plenty of detail available. There's just marvelous things you can do with differential geometry. However, if you're talking about the smallest units, the most fundamental units, the most isolated units, the lowest mass units, you need to be careful because differential geometry is going into the state machine. You're using differential geometry when you should be using finite state machines with limited resolution. And those are very different things. In differential geometry, just like space-time, emerges from this state machine, not the other way around. You don't start with differential geometry and then the state machine comes from it. Nope. Other way around. You get this set of operators that cooperating together produce these differential geometries that then become the power that we see in classical physics. Minkowski, there's two Einsteins. There's Einstein version one who felt bad. Minkowski unfortunately died very abruptly of appendicitis, and Einstein felt terrible about it. One of the reasons why Einstein felt terrible about it was that he had said some pretty blunt things about Minkowski. My famous was the my it's not the most famous one, but the one that I thought was the most pointed was the last one where Einstein made a casual comment that that Minkowski, when he made his comment about with a piece of chalk I can draw a forward axis, Einstein essentially called him chalk for brains for saying that. So, ouch! Einstein was not happy with this. He was using clocks. He was using a much more digital approach. He was saying if you don't have a clock, if you don't have a ruler, it doesn't make sense. And Minkowski took it in a totally different direction. And then, ironically, to history, they later converted. But Einstein was not real keen on this world lines idea at first. At first. Now, I'm going to put in enough of that. I've grouched about some of that in the past, but again, this is something that physics needs to get away from. We need to get to an SMU model. We need to get a state machine universe. Gravity. This is just a little intro, real quick. But gravity transforms within the state machine. And now this is something I haven't got the math. I'll have the math in some later ones here. But if you think about it, everything I've said about these fermions means that if you're using an SMU, using a state machine universe, relativistic mass becomes real because you no longer have this total relativity between, this frame's absolutely as good as the other. No, they all become subsets, and those subsets have enormous energies attached to them. So if you accelerate a spaceship to near the speed of light, that energy is attached to that spaceship. It's not attached to the space in between. It's not attached in some it's right there. You have increased the mass of every electron on that spaceship. This presents an interesting question, which an experiment that no one's been able to do because we don't have those kind of velocities available to us. Or maybe we can be. But if you accelerated an experiment using two masses, an old experiment, capital M and lowercase m, you see how much they attract each other. Well, if you're doing this, and here's the question. If you're doing this in a spaceship that's going at 0.866 C, do you see that extra relativistic mass or don't you? Do those pieces of those balls, do they attract each other faster or don't they? And you go like, well, okay, if the mass is actually there in the observer frame, in the larger frame I talked about before, absolutely that larger frame is going to have to see those masses attract each other faster. So what's the resolution? Well, the resolution is good old space-time interchangeability, because even though the rest frame, the encompassing frame, I don't like to use the term rest frames. There's no, it's all just scale. When you're talking about rest frame, you're usually talking about the larger inertial frame from which you accelerate it, is what you really mean. And those are multi-scale, and they're all enormous number of scales. What you're really saying is in the encompassing frame in which you observe those masses, you will see them, you should see them, this is a prediction, you will see them pulling towards each other faster. But the cool thing is that at the same time, they're also moving very fast. So from the internal perspective of the moving rocket, the ship that has the experiment, they see that length converted over into time, into an extended time, and they wind up seeing these balls approaching each other at the same slow speed they would have before. So they see no difference in the physics. Now, think about that, though. It means that gravity converts within the Lorentz transformations, which is intriguing because we think gravity is kind of like being kind of larger than special relativity. But this is the case as far as I can tell. And, one or two interesting things is going to happen. Either gravity converts within the Lorentz transforms or it doesn't. And either one of those is an interesting result, because if it transforms within those, within there, then you have gravity as, in a sense, in this context, a subset of the Lorentz transformations. And if it doesn't happen, then you have a violation of the absolute difference between frames. Either result would be extremely interesting. Okay, I'm finally, now after all that, I'm finally getting to Casimir. which again, I've beaten on Casimir multiple times. So I'm just going to summarize some of this stuff and go that. First thing I'm going to do is if you want to look at Casimir, and also just to show I'm not, I've done a little bit of reading on this topic. I've done like 2 deep dives in this topic and never been satisfied with a full set of results. So here's a few good ones. These are most recent first. There's another set. Here's a few more for you. Oh, and Lamo, I can't pronounce his name, but Steve Lamo, marvelous work they did experimentally. I mean, he's an editor at Academic now, but got a quantum journal there. But that work is just amazing work where they were able to, tease out this subtle Casimir force effect, which is a real effect. Despite everything I've just been saying, the Casimir force is a real effect. It's just you got to be careful what you mean by it. But a marvelous bit of work there and well worth pointing out. And the ancestry of the Casimir effect is not what people think. They started out with electrical emulsions, electrify. Not all of the deeper history of this is very strange. And van der Waals forces, a lot of it's just figuring out how charges like to shuffle around with each other. I've had 2 previous presentations on um, this issue, sections of those, and those are listed here. So if you want to take a look at some of that, some of these same slides are in this one though. So I'm just saying that's where I got those from. Now, Casimir effect itself. Standard Casimir, empty space has nearly infinite energy. This is what Feynman complained about his own theory. He said, wow, this doesn't seem quite right. It's hard to balance it out. People have struggled. The simplest prediction is that if you truly have infinite forces due to quantum uncertainty at small enough scales, that you should have infinite density of either infinite negative density or infinite positive density of empty space, and the whole universe collapses. And the balancing point between those two is so unbelievably thin. I remember I did a calculation once. You take the universe, you look at a proton, then you make that proton into a universe, and you take another proton, you make that proton into a universe. I think it was like, I don't know, 3 or 4 times. And then you finally get how sharp of an edge you need to keep the vacuum from collapsing due to this. So it's when I say there's a problem with the quantum field theory in this, I'm not kidding. It really goes crazy on trying to go to the finest levels of detail. So you have this attractive force, and the idea is that if you have these plates, it restricts them from bumping into each other. If you've ever been on a boat next to a dock and you put your hand in between the dock and the boat, you can get your fingers crushed because of the Casimir effect or the equivalent up in the waves. The waves will push the boat into that shadow created by the waves. These are just shadows. That's all these really are. That distance between those plates is a shadow. So the waves outside push them together. So this is where you get the idea of attractive force. But notice the attractive force is not from the gap. That's misinterpreting it. That's just a shadow. The pushing force is from the outside. It's from all the forces on the outside of the plates trying to crush the plates together. And that's a bit of a problem because if you do a real Casimir model, it's a great little video where they show this effect. If you crank up the shaker on a beaker and you have 2 plates there, you will observe the aquatic equivalent of the Casimir effect. And in order to do it, I like the way the fellow says this, Dr. DiNardo, but the way he says this is tricky because you push it near the limits before you can finally get this thing to take effect. You really have to get those waves moving. That corresponds to the nearly infinite frequencies that you have at the lower scale of these things. So it's a violent thing. And this creates an absurdity. There's no other way to describe it. If the Casimir effect was real and as described, every metal block would turn into a black hole. Why? Because every metal block would have infinite forces pushing inward on it due to that block not permitting the full range of forces to cancel out. So it's like that submarine that's at the bottom of the ocean, and it gets crushed because it's got a hole, it's got a gap in the inside. And if that's not filled in, it can't resist those forces. So this creates a concept that any metal plate, because you think about it, a metal plate has no gap at all. It's a zero gap. So that means that all the forces should come in full play. So the only way you make the Casimir effect works is if you exempt all but an incredibly tiny sliver of the waves, and which is exactly what has happened. Because you say like, well, if these waves don't work and these waves don't work and these waves don't work, but this little tiny sliver, this little tiny sliver of waves, they do that. Then you get the measured effects, and you can actually calculate out within that tiny little narrow strip. But then you gotta look at it a little closer and say, how are you doing this exemption? And this was to me, one of the funniest statements I that I recall reading in paper, because I just rolled my eyes and laughed. I said, "You got to be kidding!" Because Casimir said an original thing for very short waves like X-rays, e.g., you might have included gamma rays, extreme gamma rays, and all those other rays that go beyond that. Our plate is hardly an obstacle at all. What? What? If let me here's a question for you. If you take some metal object that you have and put it into a gamma ray machine and see if nothing happens to it, or put it in an X-ray machine and see if nothing happens to it. This is absurd. First of all, the assertion of transparency is not correct, and it also ignores all the consequences of those higher frequency waves. So it's a spacious argument to say the least, but also just funny. It's just kind of like, seriously, that's your way of saying that that's why it's so weak, is you just say, no, no, all those higher waves, they just go on right on through it. So the other consequence of that is cosmic incineration. Actually, I think I went through. Creates, first of all, it creates black holes. I skipped over that. Cosmic incineration, because the energy is going to obliterate the matter in that. This model doesn't work. It requires space to be so energetic that a material object that is in any way an impediment to that, which is pretty much any kind of matter, some degree of impediment, should be incinerated. So one of the most interesting statements from Casimir is much later, a couple of years before his passing, is I was surprised to see this, because this is something I had been working on independently of ever finding this quote, was exactly this kind of thing. As you'll see some of the pictures. Uh, and it just says that Casimir force is the last, but also most elegant trace of cohesion energy. I have an assertion. I say that that's the real Casimir talking. All the other stuff where he says like, yeah, maybe, yeah. I think he didn't believe his own excuse. I believe that he may have meant it when he wrote that paper, but after he thought about it, he said, that doesn't make any sense. You can't just say the X-rays are there and it just ignores them. That makes no sense, because everything would be obliterated. Every atom would be obliterated. All forms of matter would be obliterated. So I think Casimir figured that out pretty quickly, but he was stuck. Niels Bohr had supported him. Niels Bohr was delighted with his result. He thought it thoroughly proved his model that there's infinite energy at small scales. I don't think Casimir ever truly believed it. I think he was very cautious, and it's interesting how he didn't even like his name to be associated with this. These are the kind of things that people do when they don't really fully agree with the discussion that's been assigned to them. And I think that's a case for Casimir. So fascinating quote by Casimir, and also an important quote because it leads you to, it's important because it leads you to some explanations that make more sense. In terms of the SMU, state machine model, state machine universe excludes every aspect of Niels Bohr's interpretation of the Casimir effect. There's no space-time fabric. There's operators only. There's no infinite energies at short distances. That's just a spacious concept. Specious? I'm not even sure if I pronounced that word right. Specious concept. And more interestingly, though, is if you abandon this idea that there's this very well structured four-dimensional space-time as a given, then all of the particles that you see in standard models become emergences of some form of matter defining some combination of spatial and time characteristics. This is a complete upside down version of how we usually think of it. Think of it as matter, of persistent matter, fermionic and matter and energy combined, funding the development of interesting configurations of space-time, because space-time becomes a much more fungible asset in this model because it's just operators. So you use small scale operators that don't quite create a full definition of space-time. Half spin would be an example. That's not a full definition of space-time. Half spin is a partial definition of space-time. It's a very weird partial definition of space-time. You have rules that the particle emergences reveal the rules for guiding use, but they don't mean that those are all in operation at the same time. As an example, that protons would be extremely stable. Local space-time states, they don't have energy beyond what they're funded with, and they only show things like quarks, gluons, pions when they interact with various levels of energy with phenomena that say, oh, okay, I can do that now. I can spit that out. It's in some ways it's subtle, but it's an important distinction to make, that the idea that you have stable states that allow the emergence of complexity without actually having the complexity. The electron orbital is not a superposition of an infinite number of electrons doing a little bit of everything all at the same time. It is simply a set of rules that say, I'm here, this is as compact I can get under this set of information, this set of mass and energy. Can't do anything more, but here's what I'm capable of, if you ask me. Here's what I could do if you do that. So state machine model gives a more precise way of saying that, what is your next state that is possible if you do that? Casimir reality. If Casimir effect doesn't exist, if there's no way that you can wing it around so that you can get these infinite electromagnetic waves, then why has it been detected? Because that work that was done absolutely showed the existence of a small, very small, after you factor out van der Waals forces, which is a really interesting story all by itself. After you factor out the van der Waals, and if you factor out other things that we can explain more conventionally, you still have a lingering little bit of attraction. And that is the attraction that follows a wave-like model. Well, why would that be? One of the things I want to point out is when you're talking about metals, you are talking about substances that have electrons that exist as waves. The idea that electrons are purely little particles just doesn't work for metals. You have to use the wave model for electrons. And this is just a simple example. You've got a block of metal. You have electron states. This is standard conduction theory, standard band theory from metals and from semiconductors. So you have these different wave states. They have like one loop of a skip rope. You have two loops. You have three loops. It keeps increasing. If you break that block apart, you are also forcing the lower energy states to break into higher energy states. In other words, this is why metal is strong. This is why, because it doesn't want to do that. You require some energy in order to break that. Well, the fact that you put energy into it means you can get energy out of it. And this is your true source of the Casimir effect, is saying that, just as Casimir said in his later years, it's the last little bit that if you break the pieces apart, the body's going to try to pull them back together. You can release that energy that you created by putting those pieces closer together. Well, how does that work out in detail? Well, one of the other things you want to see is that there's interesting structuring, even in a block of metal. And that metal structure and that structuring of charge is very low level. It's very small. It involves, in some cases, just individual pairs of electrons, but it's still there. And what happens is electrons in the base state form, the lower left-hand model, you see where there's got just a single concentration of charge towards the center of the block. But you also have more complicated ones where you have like all eight of these things will form in that cube. So these are non-even charge distributions that form naturally as a result of the wave-like behavior of of the block of steel, of any kind of metal, especially silver. Silver is always great. Well, what does that do? It means that um, if you have these charge distributions, they form fields that extend out from the metal. And the way that this is, the fact that you have this extension of the metal, you get different degrees of attraction based on the separation of the different charges. Now, this is something, this is one of the reasons I did these deep dives is I wanted to work out the math of this in full detail. So I have not done that, so I'm leaving it at this higher level. But this part of it is quite solid, that there's going to be field distributions that have a wave-like character to them. And that wave-like character should produce a contribution beyond the van der Waals forces that looks like it was produced by waves, but it is not the same thing as the frequencies of the outside quantum field theory. It is instead that last lingering attraction that Casimir talked about. This is what he was talking about. And I don't know if he ever analyzed this in more detail to get to the point of saying like, oh, that's what's going on. But he might have. I don't know. And it would be fascinating to find out if he ever actually published anything else that went more detail. I doubt that he did, because again, this was a very touchy topic for Casimir because he was in a bit of a bind. But he clearly thought something much more like this was going on. You can see those again, instead of on the left, you want to look on the right. So what you have is you have these loops of just different charge distributions that have come into play at different levels. They're a result of the inherently wave-like nature of conduction electrons, and they're going to mimic and give results that look a lot like frequency exclusions. So again, marvelous paper, and this people have encouraged me to do a paper on this. My apologies, I've not gotten around to doing it, but anybody wants to take a go at it, I put the references out there to help on doing this analysis. With that, we'll wrap this up. And of course, my emphasis again is I've already beaten Casimir to death. This third time I've beaten on Casimir. So I'm going to beat on a different topic. Minkowski space is a math error. It must be deprecated. It needs to be abandoned. And how's that for blunt? But I don't see any way around it. And it wasn't Minkowski's fault. This was a subtle error that came in to him from Einstein, who also did not notice that there was a very subtle error in a simple assumption he made one line of one paper in 1907, but then followed up on it and kept that as essentially a bug in the math. In computer science viewpoint, this is an interesting issue about bugs. You get one bug deep in your math, and wow, in your code, and all sorts of interesting things can be a consequence. So we need to go to something much more like the tilted block model, in which everything starts from the same state. You're simply tilting the states. You're changing the things. It is a physical operation. Nothing goes into the past. You're creating new definitions of space and time, but it's not magic. It's localized. And you always have a full Euclidean definition, just as CERN does for its relativistic particles, in which you embed the results fully in the larger lab definition of spacetime. Lab being a bit of a pun there. The latest it's the latest bubble, but it's also just a lab. The intentional acronym collision there. We need to recognize the role of information and the finite nature of information much more precisely to get better explanations of some of what's going on in quantum mechanics. And if we understand the information more, we can understand better the parts that don't match up with our usual definitions of finite limits in spacetime, because these things are interacting in some fashion that defies our usual definitions of finite time. Information is the quantity that places us into a finite universe and makes this state machine possible. We have an interesting paradox here. The very limits that information imposes are what make our universe possible and make it possible for us to talk about this stuff. So it's like, wow, it's an interesting conundrum. So what can you do and how much can you do it if you get below that level to the physics where all of these things are talking to each other to some degree in some fashion that we don't understand. Quantum field theory, the idea that intergalactic space is full of an ether, which is what quantum field theory really does. It recreates an ether, and we can pretend it doesn't all we want, but it recreates an ether. We got to get rid of that ether, but that throws us into a very different world in which interactions don't follow the limits we would expect. Somehow a photon gets emitted at a different distance star. It doesn't really exactly cross the empty space in between, but it does have a finite amount of time before it's allowed to interact with a whole bunch of things that are on the periphery of that. And just the idea of going to an SMU, to a state machine universe, allows us to explore things like that, I think, in a very different way. So we stop using this idea of we got to get away from the ether. And again, this is the problem with quantum field theory. It is an ether theory. Just look at it. It fills space with little devices that vibrate. That's an ether. So we need to get away from that. It may put us in weird turf, but we need to get out. Casimir's, the interpretation that Casimir effect was a proof of infinite energy at small distances was a terrible misdirection of a lot of effort because, first of all, it just experimentally, Casimir said it before I ever said it, long before I ever said it, is that no, it's just bonding energy. That's all. It's structured in a way that looks like waves, fine, but it's just bonding energy. It's not an insight. It doesn't prove, if anything, it proves that there is finite energy. It says that no, that's all you get. It's this tiny, tiny little pittance of energy that was stored when you broke the blocks apart. So that should not be made the foundation of decades, even a century of mathematical analysis. We need to get away from that and to stop making infinities at these low levels and get to something more like a state machine model. And with that, I am finished.
Thank you for the talk. I noticed Robert Baker, he has 4 questions. Can you unmute and ask yourself?
Yes, I got to get the stop share. There we go.
Yes, there you go. Yes. Yeah. Can you ask the 4 questions online?
Uh, yes, I can. Well, I did put the 4 questions there. I can ask them verbally if you want. Whatever is easier. I didn't want to interrupt, and I don't.
How about verbally?
Okay, I
Yes.
don't seem to
Yes.
have one of those hand raised flags on my setup here, so I had to put it in chat. Okay, I guess
I
in
think it's
first one,
under React or
okay,
something.
now I can't
Uh,
hear you.
I think it's under React.
Oh, it's under Real. Oh, that's what that is. Oh, okay. Thank you. I'm not used to using Zoom. I'm used to using Teams and things like that. All right. First one was you mentioned in one of the earlier slides that the fermionic universe, I think, is the state machine universe. And so it occurred to me, if that is true, then what is the bosonic universe? We know
Bosonic universe.
photons exist, they're bosons. We believe gravitons exist. In fact, there's even an experiment proposed to detect single gravitons. We believe from particle physics, experimental particle physics, that intermediate vector bosons exist. So, is there a difference between a fermionic universe and a bosonic universe in your conception?
The reason I emphasize fermionic is that without the fermionic half-spin property of exclusion, you can't construct a full system that encodes information in you get the scale-free universe where it's very difficult to define a persistent definition of information. Now, if you have some fermionic content, at least a little tiny bit of fermionic content, then you have this ability to configure the bosonic components into all sorts of information. We do that all the time. We broadcast on radio waves. We send enormous amounts of information using light over fiber optic cables. But what you want to notice is that in order to enable those, it seems to be the case that we have to have at least a little smidge of this fermionic property to do that. So all the things you mentioned about that you have gravitons, these are I haven't seen the part about the gravitons, but gravitational experiments where you get particle. At some point, we should get some quantization of gravitational forces. So yeah, that stays the same. It just says that
In my own work from decades and decades ago, I had proposed gravitomagnetic flux quantization, but these modern experiments more recently, they actually are looking for single gravitons. They're trying to do a single graviton detection similar to single photon optics. So that's why I had mentioned that. But that's an interesting point you raised there about the information. So basically, you're not excluding bosons. You're not saying that bosons are incompatible with your
oh no,
SMU
no,
model. Simply
not at
that
all,
in order
not
to
at all.
have an information content, you would need to have fermionic content,
Right.
fermionic content to it. All right, that's interesting. That's an interesting point. Okay. Uh, okay. Next one was yeah, I in the DAU, what I've looked for in work like that, in kind of very innovative work like this is I try to, and there's no insult to the author, of course, but I try to see, are there any tautologies in there? In other words, is there any assumptions being made which are actually being that which is either being asserted or proven by the model. So in this case here, we're basically saying that space and time even as concepts at all is emergent from the state machine conception, the state machine operations, activity as illustrated in your DAU diagrams. So what I notice on the bottom, of course, there's an axis where you have these arrows, even in the rest case scenario, you have these vertical arrows in staged right, next to each other, marching across the bottom axis, which you call distance. And so my question was, what actually are each of those arrows? Are they associated with you can't say they're associated with a point in space because in your conception that does not exist, or at least does not exist primordially. Are they associated with a piece of matter? Are
Yes.
they associated with the what
Yes.
so you're saying that these are little pieces of matter that are arrayed non-overlapping. We could use topological terminology. You're probably familiar with T0, T1, T2, T3 topologies, separation topologies. You could probably define that topologically. It might be a good idea to do so to make it mathematically precise. But so those are little pieces of matters. They could be must be all the same scale. Can one have a particle next to a rocket ship, next to a galaxy, next to a particle? Or what is the how are those things staged? Are we assuming that there's a kind of an equivalence class of items that constitute that array of arrows?
The scale can be multiple scale and can include different size units of matter. When I showed the picture of the CERN facility tracking individual particles, that's an example of two different size scales of matter units operating under the same DAU. So you have a finite amount of time that passes in the CERN facility, and you have a finite amount of time that you place in the operation of that particular particle. Now, usually you're going to want to break it down to a smaller level for the particle, but you can do that. You can take, the units do not have to be the same size. You do need to have the same definition of the embedding frame time. It defines the length of your unit. So you pick a quantity for your largest embedding frame, your lab frame. You say, I'm going to use an hour, I'm going to use a nanosecond, I'm going to use whatever unit of time you want. And that defines the length of the operator that then applies to all units within that system. And the assumption is, and again, it is an assumption, but it's one that tracks very well with the actual behavior we see, is that you have this inevitable velocity that you can either loop or extend in one direction. And then that is the angle of the DA unit for this. So multiple scales, again, it's a matter of what you can find as a unit that makes sense for the context that you're doing. If you're doing a large laboratory, you want to have one large DAU unit. For the laboratory, you might have it over a short distance. Number of ways you can configure it. So
Okay, that raises an interesting. So in the CERN case, the multi-scales, you have the particles being measured or tracked on the one hand, then you got the gigantic experimental apparatus on the other hand as part of that. That's the, would that be roughly the multi-scale you're talking about there?
yeah, there's in that case, you're probably going to want to be using laboratory scale DAU units. You're saying you're making the increment size something that's appropriate for the laboratory, but then you're tracking a much smaller unit of matter within that and watching how it behaves with that. So you wind up with pretty much what you see in those kinds of tracks. You see the increments forming the different locations, the different isolations of the particle in the bubble chamber. Those become the little increments of whatever DAU unit that you're using, because you want to have a fairly small DAU unit for the laboratory as a whole. Uh, the the concept that really kind of drives it is just keeping this idea that you'd never lose the time and space definition of the embedding laboratory coordinates. They're still there. And again, CERN is just a beautiful example of that, that these particles are behaving in all sorts of relativistic ways, but it doesn't really matter. You can see it. When we use spaceship examples, I think we're too prone to thinking that the spaceship can just whiz by and we pretend that we can't see it. That's not a good model. Einstein himself derived the time dilation effect by making sure you tracked and you touched every piece of that whatever the object was as it moved by. That's how he figured it out. That's how he figured out that time dilation was real. So we can always instrument different levels. And this is just, the state machine just gives a convenient way of saying that instantly puts limits on the fact that you have to attach every DAU to a material. When I say material, I mean mass and energy. It's fine if it, again, a little smidge of fermionic matter goes a long way. It can have a lot of energy associated with it, but you have to have some kind of the fermionic matter is the one that most defines the idea of a definition of time. That says that this is where I want to go if I'm just sitting there at rest.
It was, well, speaking of time, is there, you mentioned loops in terms of time, with time for basically rest, stationary. Uh, is there a concept in your concept akin to what differential geometry for general relativity, for example, would be called the CTC, a closed time-like curve? Are there such loops within your SMU
That
conception?
one at this point, I've tried to avoid the curvature of space issue because unavoidably it says that curvature of space has to be a set of relationship between mass energy systems. So it does just as it did for the other parts. It says that these are relationships. But the curvature is a fascinating issue, and you're going to emerge. It doesn't, you don't get rid of curvature concepts, but you do transform the attachment of those concepts to matter itself. So the state machine model uh, unavoidably says that even on a black hole, that black hole still has to remain attached to fermionic matter. And I've addressed this in some early presentations, but even though the overt behavior of a black hole is exactly what's predicted by general relativity, we've seen that experimentally, although with some catches. Some of the things that we thought fell into the black hole haven't fallen into it yet is a noticeable example experimentally. Uh, but that says that the matter of that black hole still exists in some fashion and is on the event horizon surface. So the overt characteristics from a distance of the black hole look the same, but the actual dynamics inside would be very different. And that's an example of where that would affect the curvature issues. You don't wind up with singularities at the center of a black hole. So a lot of interesting issues, and again, that's
Okay. Let's see. Next, last of two, you actually raised it a moment ago. Relationship between the SMU and matter energy. as I understand it, the SMU is what I would call a substratum concept relative to what we think of classical physics or even quantum physics, matter energy. Yet at the same time, it's ineluctably tied to matter energy. So uh, which concept comes first? Or to put it another way, is matter energy emergent from the state machine, or vice versa? How does matter store the state machine, as you say? Uh, I think that's actually your term from earlier in the lecture. How does matter store the state machine, and which is emergent from the other, or are they both co-emergent?
Co-emergent is the term I would use for it because the properties of matter on how matter interacts with itself are, yeah, powerfully a part of how this works. Now, yeah, in quantum physics, if you're familiar with the idea of decoherence, I like the idea of decoherence up to a point, but I think it's overly complicated. My own way of saying decoherence is bumping. That whenever you bump an object, you actually collapse what we would think of as a wave function. So the bumping idea in decoherence, the more you bump into things, the more you restrict the definition of the wave characteristics of that. If you did not have this kind of, and again, I'm grantedly absolutely a heretic on this point. I think wave observation and collapse is the most common operation in the universe and is actually the basis of classical matter. That without it, if you didn't have the proton continually observing the electron continually observing the proton, you wouldn't have an atom. And when I say observing, I mean they're accelerating each other. When you accelerate each other, and it has an interesting connection with this whole idea of frames. Acceleration is changing the inertial frame of the other particle. So items like atoms depend enormously on what we would think of as quantum observation, but at an extremely simple level. If I accelerate something else, I cause its wave to collapse. That collapsing process is where you get this marvelous idea of matter that can exist and have this spatial definition, this difference. So I would say it's co-emergent in the sense that somewhere the reality configured itself so it could sort of like keep banging on its own head at a very small level, and that banging operation, that acceleration process, is continually allowing things to have an existence. You take that same atom, you throw it out in empty space. The proton and the electron still know where they are. They're still accelerating each other. But until some larger entity, some larger frame touches that atom again, it's a wave, or it's what we interpret as a wave. I mean, that's a really interesting issue about just what a wave is an ether-free universe. The idea of a wave in an ether-free universe gets really interesting. But that atom again becomes quantum. And we see this in some of the quantum mechanical thought problems. You see a large molecule equal to about 4 DNA codons can go through 2 slits at once. Well, how's that possible? The molecule sees itself. It accelerates itself. It has an internal structure. But the presence of that structure in the larger frame can be ambiguous. If there's no bumping, things get very wonky with this definition of space and time. That's where you get these things like interference, even of fairly large molecules. So quantum perturbation, which fascinatingly goes right back to this idea of what is acceleration, because acceleration then becomes observation at an incredible range of scales, not just tiny, gives us this state machine, gives us this ability to localize, to suddenly not just be a nebulous set of things. And I think that's certainly an area I would really want to look at more closely. As I mentioned the idea before, I think there's a symmetry break of some kind going on. There is a disruption between what we think of as momentum energy space and time distance space. I think at one time in the infrastructure of the universe, those things were equivalent, that they were actually had the same properties. So I think there's a intriguing possibility that that's the symmetry break that allowed these things to co-emerge and enable the distance concept that makes the state machine substrate possible, and also the time concept that which you can change the state machine. Meanwhile, the momentum space plays this kind of bizarre maintenance role of keeping these things going and preserving the energy. So fascinating possibilities on that. Co-emergent.
All right. That is fascinating. One can even muse on when you mentioned symmetry breaking. I think of symmetry breaking differently, but if you think of momentum space symmetry breaking, when other areas of physics, including quantum field theory and group theory, applied to it, of course, symmetry breaking implies emergent, essentially mass creation, basically. Like as like a Higgs type mechanism. So one might wonder if in your model whether you might get mass, real mass in your case, out of this apparent symmetry breaking between the momentum, would you say momentum and space? So that's just
Yeah, yeah.
conceptual speculation. That's nothing solid.
And I would the symmetry breaking, the difference on it would be that the symmetry breaking, well, not a difference, but symmetry breaking would be attached to the individual units of matter. So again, there's no broad space concept, but there's something going on where some kind of thing, because obviously we're here, is breaking apart in this fashion that produces new behaviors. So yeah.
Okay. Finally, a last question. I apologize to the other listeners for monopolizing the time here, but your prior comments segues nicely into this. How does entanglement fit into your SMU model?
Entanglement and also things like the double slit interference of large objects, all of these become consequences of the state machine being unable to define what we would think of as space and time. This state machine, this is where it would be interesting. A state machine has a concept of change and of storage, of separation that is not necessarily the same as what we think of as space and time. And it's very important to make that distinction. So when I say there's a state machine, I'm not saying it's a changeless machine or that it's a machine that has no concept of separation. I'm saying that the very extraordinarily precise versions of separation and change that we see that we call space-time, those are emergent from some simpler set. Now, once you say that, what happens is that issues like double slit in experiment, entanglement in general, those become cases in which the transition between that lower form of change and separation just cannot map into the classical definition of space and time. And we know this observationally to be true because we have things like entanglement. We have these strange interference effects that go on. But it's a different way of looking at it. It's just saying that the problem is that you cannot construct a space-time capable of accommodating those results that you observed. Those results don't fit your model because they were done at a substrate level that's more in the state machine and less into the emergent behavior that we like. We don't just like it; we wouldn't be here without it. I've said this before on other ones that classical physics should not be derided as an old way of thinking. If it wasn't for the emergence of classical physics, we wouldn't be here. Classical physics gives us particles by this incessant collapse of the wave functions that probably shouldn't be happening in a fully symmetric universe. It gives us this ability to expect things to stay stable. It gives us more than anything the ability to store something called information, the idea of persistence of configurations over time. All that comes with the emergence of classical physics from this substrate. And one of the things I would really like to have a better feel for is how that substrate works, because in that substrate, our usual definitions of separation don't apply. And another example I give beyond entanglement, when you say this electron on the other side of the universe is identical to an electron here, what does that statement even mean? Does it mean they were actually literally replicated, or was just the image of a single electron relocated to an enormous span of space. I would lean towards the latter, that there's some kind of universal definition of electrons, because these things are all exactly the same. They don't evolve, they don't mutate. They're just absolutely identical across the entire universe. And that is remarkable, because if you use cloning, that doesn't happen. You get mutations. The only way you get the kind of absolute identity across the entire universe is that you have to have virtual imaging, again, using a computer science term. And I think that's a clue to us. That's a hint to us that there's a substrate that, in some perspective, you look at it, and this is actually an old Wheeler idea, that there's only one electron. That one electron is going back and forth in time, was his version. And Feynman marvelously interpreted it in a more practical way and came up with QED. But it is reminiscent of that idea that there's these relationships get set up, then information allows them to be imaged in different ways, but they still retain that deep integrity. And again, I go back to the example. If electrons were just being copied, duplicated, and spit out everywhere, in every other case in nature where that happens, you see mutation. You see them evolving. You see them changing over time, and we don't see that at the particle level of physics. So it's telling us something deep about the substrate infrastructure.
That's extremely interesting because even apart from your SMU model, I had actually raised some time ago, some years ago, the question of whether entanglement means we need to reconsider the whole concept of identical particles in statistical mechanics and quantum mechanics. It
I would agree with
is,
that.
yeah, I mean, to me, it almost implies, I'm thinking somewhat like a subway system that, which could also be considered a substratum, that there has to be some kind of an identity tag to those particles or whatever in order to have them entangle with each other and not be self-entangled, so to speak. So I do want to, that's an interesting, very interesting discussion. Yeah.
And I have to point out on that if you look at the definitions of bosons versus fermions, so just the deepest definitions of the wave function, where you got one solution gives you fermions, the other gives you your bosons. All of that is based on the idea that if there's nothing to distinguish the particles, they are the same. So our quantum physics, in a very deep way, is already based on the idea that all electrons are the same electron. It's built into the math, but I don't think we carry it to the limit of saying like, well, that's true in a tiny little system, because it absolutely is. I mean, if you have a small system, you cannot distinguish between those electrons unless there's some characteristic that's added to it, spin, orientation, something to distinguish them. That's a fascinating thing, and I think part of this broader insight that effect somehow extends to the entire universe. And again, I would invoke this breakdown, the symmetry between momentum and location. The momentum space somehow must be involved with that, but in which way, I don't know. Octonians, anybody out there who likes hyper complex numbers, look at octonians, because that would be the mathematical framework that most intuitively would break down into two asymmetric spatial definitions. So sorry, just had to elaborate a little on that.
Thank you. That's quite interesting. In fact, I would comment that as you seek to move from Minkowski to Euclidean space, at the same time that mathematical heart of that is that complex, what you call complex, the complex CRU, what did you call it? The mathematical representation of a complex
Complex.
number of the yeah. It's interesting that you kick it out of Minkowski space, but you kind of introduce it at a more fundamental level. So it's interesting that the complex element re-enters, but
Yes.
in a more substratum way, so to speak.
This was just a couple weeks ago, and this is some of this kind of fast moving. I started with tilted block models, was going over with my son, who's good at math, about different representations, matrix representations of the rotations. And then we suddenly realized that we don't need just use imaginary numbers, just use complex numbers. And all of a sudden, the entire model collapsed into a multiplication of two complex numbers. That can't be a coincidence. There's got to be some kind of connection between that formulation of special relativity and quantum mechanics, because it just seems eerie that they would come to such a simple, similar conclusion with that. And my only debatable point is I'm not sure. Again, I would love to play around with using the real axis as the time axis and the other axes as the three-dimensional time, because it still gives you that same behavior for that particular case. But I think there's some really interesting math possibilities.
All right, I yield the floor. Thank you.
Okay, thank you.
Actually, I get a question from Lou. He asks, how is this affected in an expanding universe? But I'm not sure what this he's referring to. Lou, can you unmute or can you ask a question again?
Well, that is an interesting question by itself. An expanding universe. Something we are doing in our universe has an incessant forward drive to it. And this is where I go back to that speed model. I did the intuitive thing about the speed model. You either go in loops or you go one way or you go the other way, but you got to keep moving. And that says that there's a larger structure that is expanding our universe. And actually, this is something that's coming up on one of my future videos when I talk about quantizing gravity, is I'll talk about dual universe models of quantizing gravity, because I think I am a dual universe advocate. I think that the symmetries, what they call the CPT symmetries, cannot be fully reconciled unless you wind up with two universes. And the two universes then attract each other. One analogy I like to use, you think of a virtual pair. We all hear about virtual pairs. The electron, the positron, they come together and then they go back together. Well, think of that on a cosmic scale, that you got two universes or two sets of complexity that push apart, and then one of them, or actually both of them, invent this little concept called time, in which basically they get so messed up, they go, I don't know how to cancel anymore. Crap, what am I going to do? So they just go shooting out this way, saying, I don't know how to cancel. And by the way, the cancellation I'm talking about hydrogen atoms, because when you put an electron with the positron, with an electron with positron cancels. You put an electron with a proton, everything messes up. Everything messes up. Suddenly it goes like, I can't, what? I can't cancel. So these things go shooting out with this definition of time, but eventually, they're going to have to come back together. So the expansion of the universe somehow is involved with this, and I think that's why we have this. There's structure that we're not seeing, that is a broader structure that helps create these different definitions of that. So yeah, it's a great universe, and I think not only expanding, I think eventually Penrose thinks that the universe will end in just a loss of scale. And I don't see that, because protons, electrons don't lose scale. They're persistent, nagging at that. But I do foresee a possibility of a big poof, that we come back together with the anti-universe and things go bye-bye. So, and there's probably some astronomical observations that you could make that would tend to lead to say that that's probably sooner than some of the other scenarios rather than later. So yeah, there's all sorts of interesting issues there.
And I got a question from George Sipperland. Do you have any comment in Cavendish experiment measure?
Remind me, what was Cavendish? I'm sorry, I don't remember. I remember the name. I don't remember what the experiment was. Can you remind me what it is?
Yeah, George, can you
That was
unmute?
the 18th century gravitational experiment, trying to measure
Yeah.
what was it, gravitational
Oh, that was the one I
dimensional
showed.
gravitational force, I believe it was.
That was the one I showed, wasn't it? Yeah, the Cavendish experiment. My only comment on the Cavendish experiment is I think really somebody really ought to check that experiment out in a highly accelerated frame and see if there's any detectable difference. If you had, I think that might be doable. I mean, just the idea, for instance, in International Space Lab, if somebody could do a Cavendish experiment with exquisite detail and look to say, how does all this motion and gravity affect the ability of those things to go together? I have not done a literature search on that. Usually I would have done a literature search before I even said that. I have not, because that was an idea from like 2 days ago. But I think that's an interesting issue because is gravity invariant under special relativity? I would say yes. But saying that places gravity in a different relationship with special relativity than what you might expect. And if gravity is not invariant under special relativity, wow, that's a finding all by itself. So either way, that would be an interesting experiment to see if there's detectable levels of change due to special relativity on the Cavendish experiment. No wonder that name sounded so familiar. I grabbed a more recent issue, but I was thinking like Cavendish. Anyone else?
William Slater, do you have question? You unmute.
Yeah, I've got. Can
Oh,
you hear
sure.
me? Yeah.
Yes, Dr.
Yeah.
Pan, yes.
Yeah. It's just a simple question. It's about this nature of time. If time is a kind of rate of change, and the smallest time is defined by the Planck's constant, then the infinity shouldn't exist at all. How do you perceive the role of the Planck constant on your model of state machine?
Yeah, Planck's constant. Now, do you mean Planck's constant or you mean Planck units? Or do you mean like Planck scale?
Yeah, Planck scale. Yeah.
Planck scale. Yeah,
Yeah.
because Wheeler had a concept and he had a different name for it. I don't know. It had an interesting name, Arons or something. Wheeler was the one who first came up with that. And basically, he did an extension of the calculation saying that if you take all these things to a certain scale, you should get this Planck unit that has the weight of around an amoeba or something like that. It's pretty massive. It's pretty massive, and a certain size and scale, very tiny scale. The simple answer to your question is that if you go with a state machine model in which the state is only maintained by systems of mass and energy, and all other information is excluded, which I do, which is what I'm doing, then you don't come up with Planck. You don't come up with Planck foam. You don't get Planck foam for the simple reason that you can't put enough mass energy into one spot to create an instance of Planck foam. As a conceivable limit, it still exists. So in that sense, I'm not saying that you can't have a Planck unit, but the trouble is this, that a state machine model is very rigid about the amount of information required in order to define the unit. So the amount of information that would be required to create one Planck scale unit would be comparable to the total mass estimated for that unit. So you get this fascinating thing. It's not that you couldn't create it and maybe it would have really interesting properties. The assertion is that in a finite state universe, those are not the fundamental characteristics. Those don't mean anything for the overall structure. They might give you some insights at some level, but they're not part of what's going on all the time. The all action is in the actual information that you would be having. So I won't say they're totally completely incompatible, but it certainly puts a different spin on it. It becomes just like particle accelerators. The particles you see don't occur normally, and that would be an extreme example of that.
Yeah, thank you.
Bill, did you have a question, Bill?
No, I just well, I had a question and a comment really. I put a link in there to the TCP finite state diagram, which I love because I've been involved in networking for over 30 years. But I'll work with you on if you want to on this, but I think it would be useful if you talk about finite state machines to actually show an example of this in a visual diagram.
I would agree with that. And this again, ever since the tilted block formalism, this has been kind of moving quickly in some directions I didn't quite expect. So the finite state, the FSU is only like a couple weeks old. But once I glommed onto it, I don't think I'm moving away from it because it just makes some of the the
Sure.
math so much easier. So yeah, that was a good example, and yeah, please feel free to send me some examples.
Good.
Thanks.
Wonderful job, though, Terry. Thank you so much.
Well, thank you, Bill. Anybody else?
I got a good comment from Lynn. Terry, this was a fascinating presentation. Your state machine perspective on emergent space-time resonates strongly with my own research, where I explore how a specific geometric density of space can generate the constants we observe. And Lynn will be presenting on December 20th.
Oh, okay. Look forward to seeing that. The yeah, the state machine model it's it's fun partly because it just makes some of these issues much more tractable for saying, well, if even space and time are defined by operators on models, I can do that with a computer. I can get an idea of what that looks like. So you get some really interesting modeling opportunities that you might not get in some other models. And there are cases where models that I've worked out do give slightly different results from the lead nuclei collision models that they use, for instance, at the Large Hadron Collider, because they introduce a time gradient, and the models they use don't address that time gradient. So that's getting really deep in the weeds and doing it, but it's still a real difference. And these models are ones that are tractable to computer or science background folks. So computer science could, and I didn't plan it that way. Boy, I didn't plan it that way. But there's an opportunity there.
Hey, Terry, real quick, part of the politics about how the Hadron Collider wound up in Switzerland is when the Bush 41 administration tried to get that through and put the Hadron Collider in Texas, Congress decided not to fund it. And so if Congress had funded that, if we could turn the clock back to the early 1990s, the politics of the development of science might have been a lot different. It might have actually happened in Texas instead of
I remember that.
Switzerland.
I remember that well because there's those giant holes they dug. They actually got to the point where they dug giant holes, and then they defunded it, and that was the point where the U.S. pretty much abandoned the deeper research.
Sure,
And by the way, that I love some of that research they're doing. Some of the stuff they've done with the large lead nuclei collisions, there are certain detailed characteristics. Again, I'm getting really down in the weeds,
sure.
but some of them are not well explained, and I think models. I've got to go back and look at that because I do think some of these ideas can help give some kind of explanation, maybe for some very specific characteristics that they've found in some of their data.
Sure.
So something else.
I'd also like to add, since I'm here in Chicago, two things. One is if you go look up iqmp.org, you'll see that we are putting one of the largest quantum facilities, maybe in the world, but definitely in the United States, on the south side of Chicago, where the U.S. Steel plant used to be. So that's iqmp.org. And the other thing is on, I think it was on November 3rd and 4th, we had the Chicago Quantum Summit 2025 here. And one of the things they had the deputy, the deputy director of the U.S. Department of Energy, which is where all the quantum work is happening in the federal government. And this is very, very interesting. He announced two things. One is that we're going forward, and the Trump administration is funding about $750 million and for quantum startup development. And this is very, very encouraging because basically they just came right out. They just stated it. They said, look, if you've got a quantum startup, we do not want you starving. If you're a CEO, if you make an application, if you got the right credentials and experience, we will fund you for your first year $115,000 salary, plus we will give you $150,000 in operating expenses for your first year. So this is fantastic news, and I want to emphasize that the other thing that I have knowledge of is that the Indian federal government is putting a similar $750 million into their quantum development over in India. So I just thought that it was interesting that those two numbers, $750 million, coincide. And I have a funny feeling, because I know a lot about the economy of India, that they're probably going to get a lot more for their $750 million than the US government will. But I'm very encouraged that the United States decided to play catch up against China and say, well, we're going to put our money where our mouth is because we want to lead this quantum race. So I think it's bright times for the quantum world.
I did not realize they were funding that, and I am a strong advocate of small company and individual researcher funding, giving unfettered funds where they don't have to worry about eating. Because just look at the track record. That is always where we get the really interesting innovations. The bureaucratic structure of large companies, bless their hearts, it just doesn't promote that, because you get too much internal competition. People
Right.
start worrying about, hey, you're going to damage my market if you do that, and that's a very real thing. So that's where you get your innovation. And quantum field is just I'm a bit gnarly in some aspects of the quantum, that I think we should be taking some very different perspectives on that, some of which I've just given. I think a state machine model gives a very different twist on how you might interpret that. But the computational possibilities there are just intriguing, because the universe isn't working only by conventional computing. It is most certainly not. And living organisms, I would argue at the cellular level, with the behavior of biomolecules and the way they pull this little trick of pulling certainty out of chaos, appears to be a quantum related phenomenon. And we don't understand that yet. And I just think there's just immense potential in that. And clever minds, individuals, unfettered, able to look at it and say, what's going on here? So I'm glad to hear that there's funding going to that. I think that's has potential.
And I got a question from Ron. Is the state machine model deterministic or non-deterministic state machine?
It is deterministic at large scales to the degree that we can perceive it. In other words, when you get into the classical approximation, so this is kind of like 1900s physics. At that level, it becomes, in fact, that's one of the reasons why they were so sure they had physics wrapped up, is because basically they were looking at a state machine-like model of, you got the rules of physics, you got the matter and energy, you do the transformations, and there you go. So a state machine model, in some ways, is not that radical, because that's kind of where they were at back at the end of the 1900s, the 1800s. Why do we have to use one number difference on our century and late? Okay, so but around late 1800s, that's where physics was going. So the trick is that you got to be very careful when you get small levels, because the quantum uncertainty in a state model is just lack of definition. And again, I would say now it is more complicated than that, but it's just saying that if you get too small, then you start getting fragmented spacetimes. You start getting non-interacting spacetimes. You get structures like, again, the spin 1/2 particle, I would say, is an actual instance of spacetime, and that's a heretical statement. But after looking at spin issues, I'm also quite convinced that that's part of why it works. It has its own definition of rules that are different from the rest of us, and then you get these things going. So small scale, no, it's not deterministic. Large scale, it gets more and more deterministic the more features you have that follow classical observation, but it will never get fully deterministic.
So if I could follow up on that, at the small scale, does that just mean we just don't know what the other states are? Or
It means that at the small scale that the other states don't exist. So it's a little blunter than that. This is the sparse information universe. It's saying that if you don't have enough information, there are emergent possibilities, and you always want to keep that in mind, the idea that behaviors can emerge from, like, an electron floating in space. But below that level, instead of having superpositions of infinite numbers of infinities of things, you just have a stable state, and the stable state is the state, which we haven't done, I think, a real good job of defining, but we can define the potential of that state by using particle models and by using quantum field theory and can make some marvelous predictions. So the two have a relationship, but it's important not to think that those internal things are anything more than samplings of that state. If you notice, whenever someone says that, for instance, an orbital is a superposition of an infinite number of electron states, what they always mean experimentally is if I poke it, I will see an example that looks like one of these states. If I poke it again, I'll see another example. In other words, sampling theory. So you use the sampling theory, you look at all that, and you wind up with this conclusion and say, overall, it looks like I have all these things involved in there. You want to be careful about that distinction because observationally, it never happens. You don't get all those things at once, ever. All you get is the samples. But you can use those samples to develop a model of the overall behavior. So there's this really interesting relationship between very traditional quantum field theory type things because it works. It works very well. And this idea of what is the reality of that at a lower level? Is a pion actually, is a proton actually a bunch of quarks floating together? Or is it a stable state in its own right? And I would lean towards the latter.
Thanks. I think this is fantastic. I mean, state machines are well understood by people outside of quantum physics or quantum mechanics. So this
Yep.
is really great. If I could just add a follow-on comment to Bill's mention of the Chicago Quantum Summit, which was sponsored by the Chicago Quantum Exchange and was held in the Willis Tower down in the Loop. It's a very large entity this year. It like quadrupled in size from last year. It was probably 800 people
Wow.
at this event. I was there, sat in the front row. I tried to get Governor Pritzker's autograph, but he got shoveled off pretty quickly. And I was really impressed by the gentleman that Bill mentioned, a subsecretary of Commerce, I think he was. He was very very well versed in quantum. So a lot of the money of that $700 million is going to be under the control of like the DOD or the DOE. So if you guys are, and there was one mention of a program here in Chicago based out of Argonne National Laboratory where they had like what you were talking about, Terry. If you can get hooked up with them, they pay you a salary plus give you access to their lab facility and their lab. They give you space in their lab and access to their equipment. So it's that to me was the highlight of that funding. So
Yeah,
uh,
the
you know,
cooperative access to labs, this is something we use back on the program that I was involved with. You can get some really good, you have these marvelous facilities. Sometimes they wind up not being used that much, and you get private public liaisons between those to make a good directed use. So like, for instance, some small creative innovator can get access to those to try out some wild and wonky quantum theory idea that he might not have other tried. And I encourage individual researchers to do that. Again, that's where the innovation comes from. It's just the track record is just undeniable. Smart people who have a good idea of what they want to do. It may be very different from what other people are doing, but they believe in it and they're methodical about it. It can't just be a totally random idea, but they have something where they want to go with it. I've talked to researchers who've done I remember one guy, I had to talk to him for I think a full hour on the phone before I finally glommed on to his idea. Either dumb Terry or maybe he wasn't explaining it totally clearly, a little bit of it both. But then when I realized what he was saying, I said, "Oh my gosh, that's that is gonna revolutionize that little bit of what you're doing." And by the way, that technology is now a part of every feature of the internet these days. So, but there's an opportunity there, and if you can get that kind of funding and do it, it's good possibilities. By the way,
Yeah.
I like your symbol. I always like your B symbol there.
Thank you.
Yeah. And Bill, now I'm going to have Jim Croce's Leroy Brown in my head for the rest of the day, because you start out with South Side of Chicago, and now I can't get it out of my head. So
That's hilarious.
baddest part of Quantum Town. So
Yeah, rest in
can make
peace,
it into
Jim Croce.
yeah. Okay. Other questions?
It's more, maybe not physics, perhaps more geared towards philosophy, maybe philosophical kind of question.
Oh, sure.
On earlier slides, you mentioned about the space-time fabric and its relation to energy and mass. Now, suppose that the mass and energy and mass are absolutely still, no change. That implies that the space-time fabric would collapse. Is it correct to say so?
In the way that I'm defining the state machine here, something is absolutely motionless. First of all, that can't happen, because if you take quantum oscillations into account, if you have an atom that is I, I think you can postulate an individual atom that is at absolute zero. You certainly cannot do it for a collaboration of them. You can just approach it. But if you imagine an atom or a single particle that is at the lowest energy state imaginable, it still has quantum spin. It still has the spin that we talk about, the half spin, the whole spin. That is a dynamic quantity that changes over time. So the first thing that happens is you cannot have that concept of being totally motionless. Which is why I keep emphasizing the fermions. Fermions with their half spin seem to have something critical to do with that. They provide a structuring and a separation ability. The exclusion, Pauli exclusion principle is the simple way to state it. That is critical for providing an overall solution that has retention of memory. So no, your space-time fabric would not collapse. You would still have these particles. You still, for instance, two fermions that are in the same state, they would still repel each other. And of course that would be an energy potential. So you wind up having the fermions infinitely far away from each other. You get all sorts of things, but the universe as it's given to us just does not allow fully static. We get the illusion of it when we travel only in time. We can make structures that seem very, very localized physically, but they're still moving through time. And you can, that's the speed movie model again. They wind up doing that little spinny thing and off they go. Yeah, Bill?
Yeah, thank you.
Yeah, sure. I'd like to leave you guys with a final thought. And there might be some people that come up with contributions after this, but my wife and I spent Thanksgiving a week ago in Acapulco. My wife and I don't have any kids, and we just celebrated our 25th anniversary on Wednesday. So we're we're world travelers. But let me tell you what I observed in Mexico. The people down there are just as sweet as possible. We were in Acapulco, and I want to emphasize something. I don't like to get into politics. I mean, I can talk politics, but it's never popular in a big group. Despite the tone of some of our national leaders about Mexico, those people down there have no guile or agenda toward the United States. They're just as sweet as they can be. And so it occurred to me when I came back, and I've already reached out to a guy that was in our Australian quantum group, a guy named Joseph, who's from Mexico. Those people are very hungry for the stuff that we're sharing in this very this webinar right now. And so my Espanol is poquito. I know how to be polite in Espanol and stuff, but I can't carry on an extensive conversation. But I'm very concerned. I want to make sure that our closest neighbor, Mexico, 175, 180 million people have access to the stuff that we're doing today. And so I'm going to do my best to start up some Mexican quantum user groups, because I want to make sure that we bring these people along, that there's no dividing wall between the United States and Mexico in terms of knowledge. So that's one of my little side projects. But even though I'm a Espanol impaired, I'm going to help those people because they're wonderful neighbors and they deserve our help.
That is a great idea, and that's a great idea. And again, individual innovators, and individual innovators are everywhere if given the chance.
Right.
And they cross all national boundaries. They cross all of the weird divisions that we make with each other.
Right.
It's just people who have a fascination with some problem and they can solve it, they are where you find them. So the more they have the chance to do that, the better. So I think it's a great idea. Machine translation certainly helps these days because that is an area where we've made huge progress, at least with European languages. Chinese is still a little dicey sometimes on the model of the translation, but we're making good progress on that. Also, when you said that, I couldn't help but think of the Astrophysica group that I used to participate in during COVID. Marvelous group. Roger Penrose showed up every week with us and was there asking questions. It was just a marvel. And by the way, most of the tapes with Roger Penrose on them are gone now. They got for some reason they got deleted. Yeah, seriously, they got deleted. They're not there anymore, at least not openly available. So I think it was just a terrible loss that a lot of those tapes are not there anymore. But some really fun conversations and I think good exchanges of data. It was all done in English. But I love the fact that it was, working with the observatory groups down in South America. So that kind of exchange is great. Someone said genius doesn't have a skin color. Yes, amen. Oh my gosh, the distinctions humans make on a genetic basis are so bizarre because none of these ideas people have of race really correspond to the actual genetic distributions of anything. So to say they're arbitrary, humans are very we have a very narrow gene pool actually, and you compare that there are mice that have like 20% diversity in their gene pool in their same species, and ours is like I don't know, it's incredibly tiny. So yeah, this is very artificial stuff. Yeah, Bill?
Yeah, I wanted to give you all a perspective. I was one of the founders of the Chicago chapter of the Internet Society, and so we had the bizarre experience of having a video conference up at Northwestern University with the Dr. Alejandro Pezzanti, and this happened right after 9/11. And so a lot of people, took stock and said, well, who are our real friends in this new post 9/11 world and stuff? And definitely it's Mexico. And so uh, he's talking about, well, I'm talking to you from the University of Mexico, which is known as UNAM. And he says, this was established 450 years ago. And I was polite and I said, well, Dr. Pizzanti, you said 450 years ago? And he said, yes. And I said, well, that's pretty bizarre because in the United States, we haven't, we're only about 225 years old. And so, in other words, they've had culture and art and science and stuff going on over 400 years down in Mexico.
Oh
So
yeah.
I want to emphasize that as Americans, I think we have a special responsibility, being the richest and most powerful country in the world, to kind of like reevaluate our stance on the world stage and say, wait a minute, along with great wealth and great power comes great responsibility. And we need to make sure that we are not we don't come off as arrogant to our neighbors because everybody deserves a fair shake in this world, whether they're born in a country with a GDP of less than $1 trillion, because we're about $30 trillion country. Everybody deserves a fair shake, and I think as enlightened internet citizens who participate in groups like this, that we need to be aware that we need to reach out to other people without any sort of prejudice and say, you want to learn, hey, we're here for you. We're a resource for you.
Free market intelligence is also the most powerful form of intelligence because every person who gets a solution who can then benefit, as opposed to having it taken from them, but just can benefit from having a solution. The networking effect of that, as all people work with each other's solutions, is just enormous. So there's this concept of free market intelligence that is one of the reasons why countries that allow people to do what they can do tend to have much better economies. They tend to have much more powerful use of resources because you're engaging more people with smart ideas. And it's just, it benefits everybody, including people who are extremely wealthy. And it's falling into the trap of thinking that, power for power's sake, it never works out well. You just wind up undermining everything. I'm gonna see, can we get back on physics? Any more physics questions? It's a good discussion, but there might be people still wanting. Helen, are we nearing a close here?
I'm always on, so I can keep the Zoom on until there are no more questions.
We've been 2.5 hours already.
Yeah. 2.5 is probably a reasonable shutdown limit. Great questions, everybody. I really appreciate it. Great conversations and points. So really enjoyed the session.
Yeah, I got a good comment from Jordan. Thank you, Terry. Great presentation. Lots to think about. Thanks.
Okay, thank you. Computer people out there, here's your chance to get into physics, state machines. There's a path there, and I am not kidding about that. I think there's some.
You got
some real
engineers too here, not
What's
only physicists. You got engineers.
Engineers, quantum physicists, if you're interested in a problem, you might be amazed what you can do on something like that. There's some good stories about that. So shall we wrap it up, Helen?
Sure. So thank you, Terry, again. And Terry, we have the next talk on January 17th at noon. So I posted registration on the chat. So you're welcome to sign up.
Okay. Thanks, everybody. See you guys next month.
Yes. And next week, we'll have another one about neural network on December
Oh, yes.
14th.
And you confirmed that it's at 10 a.m. Eastern?
Yes, in the morning.
Okay, I'll check I think something got messed up on my invitation. So, okay. We'll see everybody then.
See you.
Bye.